Good morning, good afternoon, uh, good evening, folks in India. So I know there are like seniors, juniors, everyone. So I'll keep it pretty sweet and short. Let me share my screen. Vikas, हम focus में क्यों हैं यार? Like, can you put the presentation in focus? Okay. Everyone share your screen. Okay, great. So, okay, intro. So just to quickly introduce ourselves, there are going to be three of us who are going to be talking. Myself, I'm Vivek. I'm from 2001 batch. Did my undergrad from ICER Pune and then my master's from Columbia University in New York. Currently work at Gap Inc. and where like I have a data science team where we work mostly on inventory analytics, which is dealing with pricing and things related to movement, supply chain, and things of that nature. Along with me, I have Parivesh, who is a batch junior to me. Parivesh, again, pretty much the same education as I had from ICER, same batch. And then again from Columbia, same program, operations research. And he's a applied scientist at Amazon, primarily focused in, well, I'll stop there. And then we also have Jayant, who is a year junior to Parivesh, so 3 batches ranging from 2001 to 2003 here. Jayant did his electrical engineering from BITS Pilani, did his master's from National University of Singapore in analytics, worked at Facebook in Singapore, then moved over to US, and then he's currently working at LinkedIn. So that's going to be 3 of us, and we are going to be talking about data science, and we have tried to cater it to the audience so that it's very easy to follow. We have tried to keep it as much English as possible. So I avoided a lot of math, and essentially, like data science is just using data to make better informed decisions, make business decisions. And what we'll do in this section is we'll go over like 3 different use cases of data science. In theory, like all 3 of us have the same profile, but as you will see, like we work on 3 completely different fields. And yeah, with that, let's just get started. Any comments to add here, Parivesh or Jayant?
I think it's good for the most part.
Yep, let's go ahead.
All right. So here, again, this is a skill matrix I have. We just want to flash this one. Don't want you to get hung up on the numbers or anything. I would say just keep these skills in mind as we go through the slide, and we'll come to this matrix towards the end again, where we'll try to contextualize each of those problems that you have gone through to a specific role. And then, so long story short, keep the skills in mind and also have this in the back of your head. Just ignore the numbers for now. We'll come to this again towards the end. And like I said, and also we can go in details about like our own journeys, like how we got to where we are right now in Q&A session. So with that, let's just get started. I will talk about pricing because that's what I have been doing for a long time. So price and price optimization, something sounds very innocuous, harmless, and like is present everywhere, right? But how do we use data science, or what are the specific use cases of data science in this field? So there are like many use cases, and I'll focus on like a handful of those. Before I go into pricing, I just wanted to like ground the audience into what pricing is. So pricing essentially, like you go to like any place, there is a sticker price to a product. Like in India, there is a MRP, which is the universal price. But if you think really about MRP is a maximum retail price, right? So a pack of Parle-G that costs 5 rupees, it should not cost 5 rupees in a far off place like Ladakh or like in Northeast. And sorry, it should cost the maximum like 5 rupees in those far off places. But if it's being sold very close to the manufacturer where the distribution costs are very low, it should be actually in theory be lower than 5, right? But chunki MRP hai, to India mein sabko MRP mein bechta hai, right? But there are situations where a same thing can have multiple prices. A very good example is the viral LinkedIn post. Jisme hota hai ki like you have a water bottle and it's sells for like $1 in airport, it sells for cents in the store, it sells like $5 at a restaurant. So you know your value and things like that, right? So that's about it. So there are multiple factors that go into deciding what is the price for a product. And here are like the most famous or most commonly occurring 5 strategies. One is a cost plus pricing. So you find your cost for your goods and services, and then you apply a flat markup on it, and that becomes your price, right? And so it's like a cost plus price marking sort of guaranteed to generate returns. Then you have a competitor-based pricing. So you are trying to enter a space where there are like multiple competitors, and you want to figure out like, okay, where should I price? So think about like, I don't know, like you're trying to manufacture a car, and then you're like, okay, I'm targeting this audience. That audience is largely captured by competitor 1 and 2. I want to skim some clientele from both of them. So you put a price somewhere in between, and that becomes your price. So you're pricing off the competitor, not on off your costs. So again, you'll try to be above your costs. The other is penetration pricing. Essentially, if you think about like Uber, the way it came to India, they started with like dirt cheap prices, even cheaper than autos. And then slowly and steadily, they started increasing the prices, right? And then there is price skimming, where you start with a high price for something, and then over a period of time, it goes down. So a good example of here, this thing is Rotimatic. For those who don't know, so like people here in US, like it's very difficult for us to roll the dough. So there is a Rotimatic where you put in flour, you put in water, and it rolls chapatis for you, and then like cooks it for you. So when it was first introduced like years ago, the sticker price was very, very high. And then eventually early adopters got onto it, and then slowly as the early adopter or the demand went down or tapered, slowly the prices have started coming down. A good example is like fashion products, like new stuff that goes into store. It's a high price, and then after some time there is low demand for it, and the prices start getting sliced, and you get to a point where like, okay, it's a markdown sale, final clearance, whatever you have. And then finally, there is like a value-based pricing, like, hey, you have a problem, you spend hundreds of thousands of dollars to solve that problem, but here is a software that like you can pay a subscription fee of $10,000, and boom, your problem will be solved, right? So there is like the perceived value of problem and how much you're paying to solve for it, right? So that's like high level of pricing. Any questions on this one before I go on? And there is no data science in here yet. Alrighty. So like I said, like you could have multiple prices for the same product, and why offer different prices, right? So if you think about it, if you offered a single price point for something, you have a price, and as you all know, like we all are sensitive with prices, right? So like people are going to cinema, right? And the tickets are 100 rupees, right? All of a sudden, because 500, the people going to cinema will go down, right? Or if it becomes like super cheap and it goes from 100 rupees to 30 rupees, then people who can afford or are willing to go to cinema at that price point increases, right? So quantity or demand for something is a contingent on price. And if you have a fixed price, you'll have sort of like a fixed demand for it. And the area under this curve that you have here, which is the dark blue line, is the revenue that you'll generate, right? Now think of the case that I talked about. Like, so if you lower the price, you already have a very high demand. If you increase the price, you have a low demand, right? And this is the equilibrium price point that we were talking about, the first price point here. So if you lower the price, here is the first block. Let me annotate it. If you see here, this part of the business is not covered in here. Similarly, this part of the business is not covered in here. So by offering multiple price points, you are able to generate additional revenue. And when you generate additional revenue, it's always good, right? So that's why you'd have a good example for having multiple price points is like the water bottle example that I talked about. Other is like, for example, like even Zoom, right? You have different tiered pricing catered to different audience. There is a free version of it, then there is a premium version of it, and you go up, the price keeps increasing, right? So that's about it. Any questions on multiple price points? Okay, I take that as a no. What are the drivers of those price points, right? So first thing is like you want to understand who wants a product at a certain price point, right? So what we call a market segment or like a micro market. What is the time of service? Do you want something at a peak hour versus non-peak hour, which used to be the Uber peak hour pricing or something to that effect? Then there are business conditions and constraints, like, hey, you want something done in California, it has very strong ESG rules or like environmental rules, so you have to pay premium for it, versus you go to Florida, it's like super cheap. Usually things are always cheaper in Florida and expensive in California. That's partly driven by like tax situation. Who is the demographic? Florida is effectively in many ways like a retirement state. Retirees go there, they have like limited disposable income. Versus people in California, like the tech pros like Jayant and Parivesh, they make a shit ton of money. They can afford to spend money, right? So you have a gentry who is like insensitive to price. You have some gentry who is sensitive to price, and that decides like what is the price point you should offer. So how do we decide on these prices? So this is the fundamental problem that in pricing we have, and there are multiple data science use cases in that. And there are like 5 I put in, and they're not just 5, there are many, many. And I'm going to be talking about just the number 1 and 3. I kept some slides in this so that someone is interested, you can go through it. And if you have questions, just feel free to reach out to us. So how do we identify different market segments so that you could offer different prices, right? And then I'll go into promotions as well. So market segment dimensions, like usually the market segmentation is done across multiple dimensions. One is like the product itself, and I'll talk through all of those. Geographic, like whether you are in affluent versus impoverished neighborhoods, you are like, how are your regulations? How much of accessibility is a concern? Like your customers, recent, frequent, and the RFM stands for recency, frequency, and monetary. So like depending on your customer, how recent they are, or how frequent they are, or how much money they spend with you. There's demographics, men versus women, kids versus young adult versus established retirees, can be anything, right? Socioeconomic, someone who is on a food stamp versus someone who is like very well off, right? So same set of people, like different set of people will have a need for like something which is very common, which you could like exploit or leverage to find like who is going to be my audience and where do I price the product, right? So if you really think about these dimensions that we have, again, like product, again, something that moves very fast, or something that is like very cheap versus very expensive, something that is like good, better, best. We call it GBB, which is like you bought a premium stuff or you bought a Chinese knockoff of it, right? The pricing can vary. So if you think about it, what is the end goal of segmentation right here? The end goal is like find very similar selling situations so that you have like little variation and you can price accurately, have a tailored price for that audience, right? And when you're finding different clusters, if you will, I want to use that word, for your entire business, there can be like sophisticated algorithms, like semi-sophisticated ones are like the clustering techniques that you'll find in many, many places. I have a slide on that, which I will skip, but you can read through it. And then there could be something which are very rules-based. Again, net of it is you could use science to make it like as sophisticated as you can get, or you can use naive models, which can get you there. So I'll just use like 2 examples here to walk you through. So let's just say we are trying to segment our customers, right? And I have customers, like each dot sort of represents a customer here. There is like a set of white dots here as well, right? And then this is blue, pink, like a navy, and then brown, right? And the dimensions that I have here are like annual income. So someone who has like 100,000 income or above, someone who is like barely making $10,000. And here is the x-axis. The y-axis is like a spending score, what percentage of their income they spend on like buying things, right? So it again ranges from 0% to 10%, 100%, right? So the simple technique that I talked about here is like the hierarchical clustering. What you can do is like you have your customers. You can say like, hey, I want my customers who are high spending and low spending. So you say like anything that is below 5 is a low spending score. Anything above high is above 0.5 is a high spending score. And then once you have those 2 set of customers, within context of those 2 set of customers, you can say like, okay, anyone who has less than $50,000 in income is a low income. Anyone who has more than 50,000 is a high income, right? You have that. And similar exercise you do for the low spending score people, like the folks here. And as you can say, you can use simple techniques to come up with these 4 clusters. which are effectively low income, high spending, which is you have income which is low, but spending is high. These light blue, sky blue clusters, right? And then you have high income and high spending score. So you have income which is high and your spending is high. So these white dots or like gray dots that you have. Similarly, you have this high income, low spending score, and then you have low income and low spending score, right? So now this is the heuristical or like a rules-based logic that will create your set of customers. Now, what I did was I also took the same set of customers and applied a clustering algorithm called KNN, K like nearest neighbors. And I said like, hey, create 5 clusters for me out of this customer base, right? And as you can clearly see, these 4 customers that we have here are here, 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 here. What this algorithm fails to do is classify these customers into one of those bins. I mean, it will do, but it will do a poor job of it because it will just take some of these customers and put in one bin versus another, right? And what the data science technique that I used here is identified a distinct set of customers, which our heuristical rules could not, right? So again, I mean, depending on your use case, you could use this and still be okay. But again, using data science, you could find a new customer base or like a set of customers for which you could have like a tailored pricing, right? So again, going back to my example where you could have multiple price points, you could use data science to come up with a new price point and hence capture a little more market. I'm sorry, I'm going back and forth within slides. So like, for example, you found that new price point for that 5th customer. Here is this additional revenue that you get, right? So data science can definitely sort of help you get to a point where you have better business outcomes. So I'll take a pause here and see if anyone had questions on the segmentation that I talked about.
Bhaiya, this is Vikas. So I just wanted to ask you that you just showed that we are getting additional revenue from that customer. But is this the same product we are selling to that person, or is it something additional value addition we are doing to that product?
It can be same thing. It can be value add product. So like that is a good question. I use the water bottle example. So you have a water bottle, you have different selling situations, right? Similarly, you can have like, let's just use an example of a car spare part, like a cabin filter, right? You can have customers who want to just buy it from like Amazon or like a store and just replace it themselves. You have customers who will go to the dealership and buy it. You'll have customers who will be like, I just can't do it, someone do it for me. So they will be like, you go to the dealership, they will replace the car filter and they will charge you for the filter and the services. And if you look at the prices for the same thing across those 3 avenues, you will see the prices are very different. And that is not because, oh, it just happened, that is by design. Like, hey, there is a set of customers who are like, hey, instead of DIY, do it for me, right? So do it for me, customer gets a very different price because those customers usually are insensitive to price, versus DIY guys are more sensitive to price. So when you go to Amazon or like Walmart or whatever, you'll find the same thing at a much lower price.
Okay.
And I'm sorry, I'm using examples from here, but like I'm fairly certain like the same thing happens back home as well. Did that answer your question, Vikas?
No, Bhaiya.
It did not.
What, Bhaiya?
I said like, did that answer your question?
Yeah.
Okay, good, great. So that's a good example of like application of data science. And we do this like at scale. We do it across all these dimensions. So sometimes we end up creating like millions and billions of segments for a customer across multiple products, right? So you have to do it at a scale. You cannot just have rules for every dimension across which you are slicing your customer. And you could do the same thing again. If you think about it, I could add one more dimension here where I do the gender in here. I could also add demographic data like, hey, so when it's 2-dimensional, it's easy to see. When you add a dimension of like gender, you can have like men versus women. This will still be easy to see. You can rotate a cube of sorts. And then I add the 4th dimension of like age, right? Like less than 25, 25 to 50 or something. All of a sudden you have 4-dimensional data. It becomes very difficult to visualize, but for machine, those things are like super easy. They can do it at scale, super fast, something that is not even intuitive to us, right? So that's something very important to point out. So with that, I'll just a quick time check. I'm like 20 minutes in already, so I will skip through this. I have a few slides on like if someone wants to read through that. I'll just quickly give another example on pricing. So there's something called association rules that we use. Again, and here are a few examples that we have. So for example, Walgreens is a like a drugstore of sorts here, which also sells like beers, diapers, and like other things. And what was found here is like customers who buy diapers are more likely to also buy beer. And this is happening like on the real data from Walgreens. So essentially, like, what this means, like daddy needs beer, right? Walmart, for example, 60% of customers who buy a Barbie doll buy one of the 3 types of candy bars. So usually when you're going to buy Barbie doll, kids are accompanying you. When you check out, you'll see candy bars, right? And people in the US can associate, like when you are at the checkout counter, you'll see candy, gums, and all those things. They're placed there by design or for a purpose, right? The kids come along with errands, and that product placement is very, very strategic. Similarly, staples, a purchase of a stapler often accompanies purchase of paper, waste baskets, paper clips, and everything. What does it tell us, right? It tells us like, hey, we have a new hire. Orbitz is again like a online travel agency. It says like, hey, it has observed that MacBook users book more expensive hotels. So what they're doing here is they're taking their customers and they're classifying them into like, hey, you buy your stuff on phone versus MacBook versus like a Windows computer or whatever. And if you are like a Mac user who can be associated with a premium user, if you will, they end up buying expensive hotels, right? So what this tells us, like, hey, you could have a different pricing strategy or a placement strategy based on who your user is, right? And this is like a fun comic or cartoon that we came across. So it is believed that like women buy 95% of greeting cards, right? Why is that happening? That is happening because it's not that the men, like we don't buy. It's not that men don't buy or don't need to buy greeting cards. It's just like it's not in our aisles, right? So we blame the supermarkets for the lack of greeting cards that we send out, right? So like if you want to sell greeting cards to men, just put it with the beers and you'll have a higher sale. This is a joke. Net of it is like the idea of association rules is product placements. Retail stores are interested in finding these kind of relationships so that they could put stuff around, right? So how does the association rule work, right? So retail stores, like I said, are often interested in like important associations. Like for example, someone who's buying a bread will also buy a milk, right? Or you have online stories, Facebooks, and this is a good segue because Jayant is going to talk about like a recommender system online, like how our Instagram or Facebook feeds looks like. It's happening because there's something called, and I'll try to keep it like as non-technical as possible. There's something called antecedents. So for example, you have a bread. That means if you buy a bread, there's a good chance that you'll buy milk. Similarly, if you buy chicken, you'll buy onion. The opposite doesn't apply. If you buy onion, that doesn't mean you're going to buy chicken. So you have to understand like what is antecedent, what is triggering the next item in the basket. That's called antecedent and consequence. And there are like fancy algorithms that just do this association rule mining. So for example, if you're a guy who likes Family Guy or Daily Show, you would be interested in Colbert Report. So the net idea here is like given a set of transactions, you'll find rules that will predict the probability that, hey, here is this item that is gonna sell given this person has bought this item 1, right? And if you think about the use cases of this again, it's like product placement, like I said, like the beer, like if you want to sell greeting cards to men, just put it with the beer. Promotion of baskets, like you could be like, hey, well, here's the caviar and here's like whatever else. Or something could be like, hey, if you're buying bread and milk together, we'll give you like a 2% discount or something like that. So you can create baskets, and we'll just look at an example of this one. And cross-selling again. Like, hey, you bought a computer, you probably want a keyboard, or you want a webcam or a mouse or something like that. So these kind of association rules like help product placement in retail store, in online stores. It can be an opportunity for cross-selling or like creating baskets and doing promotions. So I'll just stop here and say like I have added a couple of links in here if you want to read about association rules, what are the algorithms. So these first two are like more in English, and this one is more of a very mathematical research paper. So with that, like I'll just stop with last example, right? So let's just assume we wanted to buy a monitor, right? So we go to Amazon and buy a monitor. So this is the first example. Both examples, we are buying a monitor, right? So it's a 32-inch monitor and then like whatever. But if you look at what Amazon recommends at the end of it, if you have not observed it already, it usually says like, hey, frequently bought together. So it's essentially trying to cross-sell. Hey, you're buying monitor, very likely you're going to need some accessories associated with it, right? So this is a fancy, pricey computer. So it says like, okay, well, you are buying a fancy computer. So very likely you are like a person who can shell out top dollars. And it recommends an ergonomic mouse, which is $100. It says like a fancy webcam, which adjusts and does all kinds of things. And it's for like $129. Now you just selected a cheap monitor and see how the recommendations change. Your recommendations goes to Amazon Basics, like a cable, HDMI cable for $8, and a keyboard for $27, right? So it's not just happening by chance, right? So you're saying like you're classifying your customers into someone who is interested in premium computer versus like a basic computer, and depending on them, you find your so there's this segmentation that I talked about, and then depending on how they spend money, you can have things that are like cross-selling opportunities. If you recommend like a Logitech this wireless mouse combo, very likely this guy is not going to buy this. He's like top dollar spender. He's probably buy or expensing it to the company, so he'll buy ergonomic mouse. So you see like how data science is embedded in like very innocuous things that we observe in our lives pretty much every day. So with that, I'll hand it over to Jayant. And before I do that, any questions on what I have gone through? And I included some more material like churn prediction and like how do you run experiments when you develop a solution to just check if it's doing what it is doing, the proof of the pudding, like I said.
I have one question. This is Vikas again. So my question is like whatever you told us is like very business centric. So how is it very different from a business analyst? Like you are like a data scientist. So like I see that it is more about the business like, and definitely there is data like at the base of all this.
Yeah, so I mean, like I said, there will be different personas. Like if you remember in the beginning, I flashed a slide which had the skill matrix. There are different persons who are involved in this, right? So usually this kind of problem that I'm talking about, association rule mining, can be done by someone who's a data analyst or analytics person. You could have like a clustering I talked about. It can be done by like this KNN is pretty simple. It can be done by like an analytics or a entry-level data scientist, but there are like very, very fancy techniques like that involves like neural networks or something. And you'd probably like, just giving you an example here, you can have same clustering. You have multiple like algorithms that you can do that, right? And then I'm not even including neural networks. So for that, you would need someone who is more sophisticated. So the idea of this was to give a flavor of like where data science techniques can come into solving business problems. That is not to say that like fancier algorithms are more sophisticated or more precise algorithms do not exist, right? So the examples, for example, to answer your question, like the examples that I used, pretty much anyone who has like a bit of an analytics background, like a data analyst or data analytics person, can work on these problems and have reasonably decent results. And that's the persona that's like, or like entry-level data scientist. And as we go through the other examples, like, Parivesh, just go ahead and add it.
Yeah, so I just wanted to add just to this piece. Imagine that the Amazon catalog is like very, very, very big, right? So it's impossible for a human being to sit through and have all connections, deduce all connections, or have hardcore rules. So a lot of algorithms, right? They use very less data, sometimes not the data that the volume that we typically they do, but they're able to generalize on unseen cases. So assume that you have these two descriptions, right? Dell's S3221QS32, right? You could have like a completely new monitor that came along, and the algorithm should be able to understand, okay, just looking at price and something that, first of all, it's a monitor, right? So a lot of things that algorithms pick up are not explicitly programmed because that list of explicit rules is like an open set. So a lot of use cases also are involved encumbering the model to pick up things that you cannot hard code exhaustively. Yeah.
Like what you said, like, yeah, these rules have existed, but like, what if there was another monitor which was pricey and it was newly introduced in the market? Do you think Amazon will not recommend anything? They will, right? And there are like algorithms in the background that are trying to map the similarity between this monitor versus new monitor and trying to come up with a proxy of what could be the precedence for this antecedent, right? That can happen. So a good question, Vikas, definitely. And
nice.
like we try to keep it like very simple. But if someone has interest in this, and then like I said, we'll go over the personas, like who are the different people involved in this process, and what is difference between their roles, skills, and everything. So we'll go over that towards the end, but good segue into that. All right, Jayant, I can run the slides, or you can run the slides.
Please run the slide. Yeah.
Okay. So Jayant is going to talk about online platforms. So over to you, Jayant. I'll go mute.
Thanks, Vivek. So Vivek just ran through a very important area of data science. But I'm going to talk about things that we are generally more familiar with and see it in action, but we don't realize how complex it is and how much effort it takes to bring it together. And one of the things that people on this call should be intimately familiar is Instagram or Facebook, and they can open the app and see your news feed. And there are all sorts of urban legends around how the news feed is there and how it is being constructed and how it feels like magic when you see something pop up that you were probably just thinking, but it is not magic. No one's listening. And how it is done is reasonably complex. And my effort in this talk is to just give you an overview and talk about how many different types of people are involved in building a system as complex as that. And if we have time, then we can probably try to think about in a little bit depth around each system. So next slide, please. Yeah, so let's talk about the Instagram feed ranking system. So, there are billions of people on Instagram. So, and they are all creating content at the same time. And obviously, as a user, you would not like to see, update from someone who is living in, a country entirely different from you, has no relationship with you, and his life means you're not interested in that person's life. So you want to see updates that are relevant to you, that you like, that are centered around your interests, from a celebrity that you follow and things like that, right? So it is a challenging problem to create a feed like that. So the first step of the whole feed ranking system is to gather all potential posts. So for you, what is relevant to you, there is going to be a large set that can be relevant to you. And there's a fair amount of engineering involved to create data sets that are collecting posts and advertisements from accounts you follow, like posts from friends or creators. Obviously, if you like Virat Kohli's page, you want to see some updates from Virat Kohli. And it removes posts related to community guidelines. So community guidelines, it's something that the screenshot comes from Facebook page, from Facebook's own published information. So they have just mentioned community guidelines, but it's an area in its own, with its own complexities. So so this data set creation is a very engineering heavy work. A lot of data engineers, ML engineers are involved in acquiring data like this. And this has to happen at a scale that is perhaps not imaginable if you are not part of the system. Think about that. Billions of people are creating posts, and the task is to create a data set that is relevant to me, relevant to Vivek, relevant to Parida, and that relevant data set should be whittled down from billions to, let's say, a few 100,000 posts that I might be interested in. Next slide, please. So yeah, and from what the next step is probably one of the most important steps. So what's left from billions to a few 100,000s? Now the system would like to rank them, or like to predict the probability of me interacting with those posts, right? So if there is a Virat Kohli post, the model should give us an output that, hey, I'm 100% likely to like the post or comment on the post or something like that. So there is a huge recommender system at the back end. One of the best models of the world are engaged in doing things like this. So it takes into all of the data that we selected in last step, and it runs through that model, and then it tries to predict what is the likelihood of you liking that action, liking that post, commenting on that post, sharing that post, viewing that post. If it is a video, watching that video. So the model outputs a probability. So it's a number between 0 and 1. Higher, closer to 1, it means there is a higher likelihood that you're interested in that post. Now, this model is basically, I would say, nothing sort of a magic model. It's something that's, there is a lot of work goes on in maintaining, developing, and thinking about this model. A lot of different types of people are involved. For example, someone who's a data scientist, an applied scientist. To keep the model running, there would be some people who are now classified as ML engineer or ML ops people. They would be involved in maintaining the model and keep it functioning. And you also have to remember that, as soon as you open the app, you have the feed present there, right? So all of this happens at millisecond scale. So all of this transformations, ranking has to happen in millisecond scale. So, and your model has to be good enough that your users also like. Otherwise, what are you going to do? You're going to stop using Instagram and go to some other app that you find is giving you a better feed ranking, right? And I don't think Instagram would like that. So your model has to be good enough. It has to be continuously monitored, and it has to be fast. So it's a very big job. It's a very big team of really accomplished people who are trying to look at this model from different angles, how to measure its performance, what the model architecture should be, how the model should be acquiring data and including data for ranking, and how someone can make the model fast. Next slide, please. Yeah. So what the next step in that someone, the model, the overall system takes these model scores and then combines into a single numerical score for each post. So that can be like, you can take, there are 5 different actions that you can take, and you have score from all of these actions. And then you can maybe just average it and see how each post actions for me look like. So the model is predicting for me, and they can see, hey, I'm likely to interact on this particular post with an 89% probability, on this with 65% probability, and this with 54% probability. So this is the basic outline of the process, how the system is thinking about each and every post. Next slide, please. And you can see there is a lot of there are a lot of different types of posts. There are shopping videos, there are advertisements, there are reels, there are hashtags you follow. So all of these types of posts have their own ranking system. So it's very hard to make one ranking system that encompasses all type of content is being created, because that's just too much data. There's too much diversity. And like I said in the last slide, there is someone who's measuring the performance. So there must be some data scientist who measured that, hey, we cannot make a model with the performance we need if we just do one big, huge model. So let's split it up in tasks, in different tasks. Some model is specialized about video, then some model is specialized about reels, because they're such a different type of content, right? I may like to watch long blogs, but I may not like to watch reels at all, right? So the overall Instagram system should catch that behavior from me and then give me content that accordingly, right? That's the benefit of that. So all of the steps that we just talked about, they are repeated for these types of posts. Next slide, please. Yeah, so all of these, this scoring, all of these different types of content are now collected. And this, I talked about community guidelines being a huge section in its own. So what Instagram would do is that it would remove things that are not good for you in a way. So not good is a very big definition. It could involve posts that are misinformation posts, flagged by third-party fact checkers, identified by Facebook or Instagram or any other platform for that matter. And there could be posts, NSFW posts that generally is not a preference in anyone's. Let's say if there is a pornography post, then remove all of those type of things. And that is a system in its own. So to how to look at content and how to classify them into things like that. How do you identify a post that is a misinformation? How do you identify a post that is, let's say, not safe for work, or how do you identify a post that is, let's say, selling contraband? Let's say if someone is trying to do a ad for a banned substance, right? So you don't want that to show up in a people's feed. So you need a system or you need a way to find posts like that and then remove them. So there is a huge offline effort to identify posts like that, to understand what we can do to identify posts like that. And then again, there are a huge number of people involved in this type of information generation, like data scientists, data engineer, research and applied scientists, who will develop new algorithms, who will develop new ways to identify posts. Hey, this, for example, Facebook does not allow gun ads. So, hey, this ad is a gun ad. This person is trying to circumvent our policies and trying to be too clever and trying to do it in a different way. But we found that because our algorithm is better than that person's cleverness, and that algorithm was developed in association with data scientists, applied scientists, and data engineers who acquired data, who understood what the data explains, and came up with an algorithm to identify that. So that algorithm plugs into this system to identify all the posts like that and removes them from your Instagram ad. And I must say that you may have noticed that you don't get ads like that. You don't get stories like that in your Instagram feed, and Facebook is really good at that. Next slide, please. Yeah, so the so far I've talked about how each post, each piece of content is scored, is ranked, is identified as a good or bad. But the system now has the responsibility of ensuring that your whole feed is made up of different types of things. I like Virat Kohli. I might have, he's also posting very frequently, so there is a chance that all of my feed posts are recommendations of Virat Kohli's post or Cristiano Ronaldo's post. If these are very highly followed and liked celebrities, so your feed may be spammed by posts from one person, but that's not ideal. Nobody likes that. So the feed has to be diverse. So there are some additional rules imposed on top of whatever content generation we have done, whatever ranking we have done, so that no more than 3 posts in a row from the same account. So that's why you see that there can be, if Virat Kohli made 3 posts just now, there can be some delay in all of those 3 posts to show up in your feed. So yeah, so I must say, so this is something that is a product. These type of rules are generally a product of a lot of analysis that happens in the background. Some data scientist is obsessing about data, is looking into it and doing experiments to understand, hey, when people start to feel that, hey, this is too much content from the same person. Is it 3 posts? Is it 4 posts? Nobody woke up and had an Akashvani that, hey, this rule should have that 3 posts, right? It's a product of extensive research. Somebody might have thought about deeply that, hey, what happens if people see 4 posts? What happens if people see 2 posts? 3 is the optimum, where it seems that people are okay seeing 3 posts, and after 4, they start seeing the fatigue sets in. So you can see how much work happens in the background to make this type of rule a reality. Next slide, please. Yeah, and the last step is that the system combines all the posts together and delivers in your feed. So all of this is happening in millisecond, and all of this millisecond action is backed by hours and hours and hours of hard work of many data scientists, ML engineers, data engineers, and research scientists like Parivesh. The next slide, please. And one of the main things, one of the very important aspects of all of this online platforms is that we need to do online experiments. And why do we need to do online experiments? People might think of experiments as somewhat sinister in online context, but it really is not. As a human being, all of us can analyze data to an extent. So I can do analysis of millions of users' data, several millions of users' data even. But our algorithms have some limitations that, hey, and there will be some limitation on the compute available as a single user, that, hey, can I calculate mean for a particular variable for 100 million users? Yes, I can. Will it take small amount of time? Not necessarily. Depends on where you work and what type of infrastructure you have. If I compare means of 100 million users of variable A and 100 million users of variable B, will I get a meaningful insight? Not necessarily, because at such large samples, the rules of statistics are very, very different. Let's say if I were to compare means of 100 people. So you can very easily land on a wrong type of conclusion, launch a product that is definitely not good for users. And it can wreck your company, it can wreck your user experience. So how are we supposed to understand if it is good for users, right? If we can come to wrong conclusions when we are doing analysis, there's only one way to do it, that you can do experiment. And experiment is you roll out a feature to a small section of users, and you can measure some metrics, you can measure the impact on users, and your analysis is on millions of users, but you actually may have more users than you analyze on, and they might want entirely different things that you can discover in times of in experiment. So you put 50% of users in control, you put 50% of users on the new system with a new feature, and analyze the differences. And this is also an area in itself. There are data scientists who are specialized in experiment, who think about experiments in different way, that, hey, this is an online experiment. It is the characteristics of experiment are these, and this experiment is getting interference from other experiments. So how should we come up with an algorithm to measure cleanly the effect of this experiment? So all of this is also a specialized area. And those people are also generally called data scientists with a focus on experiments. And this screenshots are from a paper published by Microsoft, and the author of the paper is recognized as a scientist who has pioneered several way of doing experiments, measuring experiments, and is definitely a well-known name in the area of online experiments. So on the right side, you can see one example of what type of features are tested. So this is from MSN homepage. Obviously, this is an example from some time back. The left side is control. So people who were put in control, they are just seeing this widgets on the left-hand side. They're just shopping. And on the right-hand side, the people who are put in treatment are seeing the right column. It's just not just shopping, it has offers, and it has a lot of ads which are different from the advertisements that you see in the shopping bucket. So these offers might be very well received by users, might not be very well received by users, but we will only know it actually if we put it in wild. So the experiments are a good way of putting these features out in the wild, and make sure that your users like it and your company also benefits from it. And it is a win-win situation for both of them. So I hope that makes experiments also kind of an appealing area for someone who's looking into it. It's very mathematical, but it's very exciting at the same time. And It's probably one of the most principled way of looking at the world. So over to you, Parivesh. Thank you very much. Yeah, and there are some links for similar systems across the internet. There are so many online platforms like Pinterest. There's Google search. There's now there are online fashion customizer models, so you can just read about them. And as usual, you can always reach out to us if you have questions. Or any questions so far?
Hi, Jayant. You discussed about feed ranking, and you said that for each post the score is calculated. So is this done for each user individually, or we cluster the user in some group and then calculate that score for that cluster, and then
It's done for each user individually. Yeah. So you can imagine how important that task is and how compute intensive that task is.
Yep.
Over to you, Parivesh.
Yeah, so two tough facts to follow, and we are nearing the closing time, so please bear with me. I'll try to keep things within limit. The only fruit I can kind of daggle at you guys is that I'll try to demystify a little bit of like things around GPT-4 and stuff like that. So yeah, so like this is a classic excerpt from Alice in Wonderland, where Alice goes and asks, would you tell me please which way I ought to go from here? And then the guy says, that depends a good deal on where you want to go. Then Alice says, I don't much care where, then it doesn't matter which way you go. So unfortunately, the users now are not very naive. So this means that search is not as trivial as it seems sometimes. Over to the next slide. So I'll try to first we'll try to highlight some of the subtle aspects of search in general. A lot of these things are manifested in how you search, each of us. So I don't think it will take a lot of imagination to see through some of these things. So for example, why is search hard? So people search in different languages. They plug in incoherent, poorly formulated queries, but they still want very interpretable and actionable answers. And that also on a very wide range of subjects. And not just that, they search through different modes. So one might be plugging in text on a search bar. Another one might be interested in talking to the system and having the system spit out answers. And the answers that should come out should also make sense. So for example, if I'm talking to a system, I would like to hear. Likewise, if I'm searching in a bar, I might like to see an amalgamation of text or image or what have you. So and to make things even more complex, like Jayant has talked about, I think there's an imminent need to get these answers very fast. And also, I think there are other small other aspects which are very vital, is like the search should be inclusive, meaning that search should cater to users of different kinds. That's the holy grail of search, and search always claims that they're trying to move closer and closer to it. But it's up to us to see where we are. So definitely massive strides have been made, but we are not there yet. Over to the next slide. So yeah, so this is something that I did last night. So for example, a very banal search would mean like you just plug in Elon Musk and Elon Musk comes out. But on the right hand side, you can say, if you wrote something in Hindi, Tesla ka main aadmi kaun hai? And still the algorithm is able to understand probably is Elon. Not just that, if you look at the second result in that page, you will see SpaceX ke boss Elon Musk kaise bane. This means that the algorithm is able to take your Hindi query written in English and spit out results that still make sense. Not just that, I think the magic of that is like, if you just wrote CEO of Tesla, it still needs to understand that I don't want to go and look. Previously, the search was like, okay, they would have gone through tomes of articles and seen where CEO and Tesla are together, and they would have spitted out that. But we have come very far. We now need to understand that if someone is asking for CEO of Tesla, they want to see something about Elon. Other thing that I wanted you to show, to note in these three is that the way the layout is. So for example, the first layout would be like, okay, if the buyer is asking about Elon Musk, maybe I want to give him a snapshot of where he works, what he does, blah, blah, blah. So on the right-hand side is completely powered by graphs, for example. Thankfully, Elon was not in news last night, but if he was, which he often is, then you would have seen like, a gazillion of news articles also showing up at the very top of the page. And to highlight that point, I actually plugged in Modi, for example, and you can see that, Google was able to understand it probably because it is news, I should bubble up news articles corresponding to Modi. So I think, the thing is how to customize and personalize search based on global themes, user themes, what have you. So I think some of these slides kind of are evocative of the different ways in which we search and in different ways in which the results are served to us. Over to the next slide, please. Yeah, we can go to the next one. Yeah, and to kind of belabor the point again, but I hope you find all of these things very interesting. Is like if you wrote yellow striped shirt, you wouldn't want articles talking about yellow striped shirts. More often, probably, you're trying to buy one. So the algorithm is trying to look through its catalog of images and trying to spit out all the shirts that are probably yellow and have stripes in them. I find this fascinating. Likewise, if you wrote Palo Alto to San Francisco, it's trying to understand your intent and it's trying to show, okay, for example, maybe the guy is interested to know how far how these two places are. And maybe the next organic step could be, he wants to jump into a car and drive all the way. So maybe he will need a Google map link to go with it. Right. So the search, right, is trying to be more and more immersive and is trying to interact with you. Likewise, if you actually a person was like a complete effete and couldn't write properly and wrote, and maybe he was Spanish. So if you wrote Raul Gandhi or something, right, any morphism of those two words, the algorithm is trying to kind of tell you, either trying to look for Rahul Gandhi, for example, or Rahul Goni or Ralph Gindi, right, all these kind of things. But still it is, or those did you mean is ranked. If you that ranking is very subtle, as you can imagine. Okay, over to the next one.
Yep, and just to add there, it's in context of like your previous search of Modi. If you had not put Modi, then someone else would have been the "Did you mean first guy?"
Exactly. So for example, so now I want to just very quickly go over some of these things. Hopefully you this will appeal to you. So for example, the query intent is critical. If you understand query intent, then you will be able to show what kind of things I should show. So for example, a man searches for this term Delhi to Kolkata. So should I show a route? Should I actually bubble up a booking portal? Right. So what should I bubble up as? It doesn't just end at showing what Delhi to Kolkata means. It shows what actionable thing I can bubble up. Likewise, the semantic understanding. So for example, if I just looked at or search for cat, but let's say, in a hypothetical world, there were not enough articles about cat, but there were a lot of articles about feline. Then the algorithm should be able to understand, okay, the guy is as interested in cat, very likely feline articles correspond to cat, so I should bubble up those results. So semantic understanding of, your search term is also critical. Likewise, as I showed, right, multimodal search, meaning that yellow striped shirt should not only spit out text articles, but it should actually show images. And you have not even written, show me images of yellow striped shirts. So meaning that you should understand the intent plus take a decision to show something in a different mode than the query itself. Likewise, that holy grail of once you get results, it doesn't end there. You want to rank them. So relevance. Then maybe, the person has not crafted a query properly, and you still need to tell him what the result should be. So maybe there will be a spelling correction team that will try to work take a very perturbed query and try to move it towards a correct version of it, so that you can subsequent things in the pipeline can work properly. Likewise, as Jayant also touched, right, there's always a need for suppressing irrelevant or offensive results, right? For example, results should not be based on rumors. I remember once, someone probably plugged in most sinister man on the planet, and probably, someone had made during a campaign something about Modi, so that was bubbling up as Google image search. So that tells you that, of course, these things are not perfect, but the intent is always to automatically suppress stuff like, for example, a fake news article. Likewise, right, conversational search is critical, maybe for visually impaired people who are not fluent in English. immersive, as I showed you, right? That it should be able to lead you to better and better experiences. Although you started with a query, but it wants to engage with you. And GPT-4 and these other experiences are a step in that direction. Engineering aspects, of course, are very important. Like Jayant talked about, is like these things should be performant. Nobody's gonna like twiddle their thumb for 5 minutes waiting for answers to arrive. Although we all take a lot of time to solve something. So search should be performant, and how to serve these big models that work really well in the real world. And another use case could be, let's say you are very picky about what data to send to a cloud platform for results to come back. So there are use cases where you, let's say, want to do everything on your phone and you don't want to, your data to ever leave your phone, but still want to leverage an ML model's magic. So then what kind of extra burden, what does that entail, for example? Likewise, multilingual requirements, as one can say, right? You want these search things to work on esoteric languages also. For example, Pali, which UPSC also takes, probably it's also an elective there. So yeah, we want search also needs to be like UPSC. Over to the next one. So now, the magic behind, I just wanted to do, of course, it's not possible to go into the details of every single thing, but I just wanted to understand. I always wondered when I started that, how does an algorithm even understand, let's say, an image or a text? So some of the anatomy of a general AI problem is like, how can algorithms actually understand inputs like sentences or images? And how do we ensure that algorithms actually understand that, what things are similar? So how does an algorithm understand all pictures of Modi, even though nobody explicitly goes and says Modi, Modi, Modi for every single image, right? So, and then, how do things how do they nowadays, if you see, like, there's an uncanny resemblance in the beards of Rahul Gandhi and Modi, for example. But how does the model not get tricked and, even misclassify Rahul Gandhi's image as Modi, right? And then how do you learn from feedback, even though sometimes feedback collection might not be explicitly built into the system? So there are like indirect metrics to measure how good your search is doing. And then how do you dynamically interact with user interaction? And then how to keep the models relevant and fresh? That dot ellipsis at the very end means that the questions galore doesn't end. So there are many, many, many questions I couldn't fit in here. So like you say, right? So one way is like, let's say you take this image and the way to, first of all, represent that as a bunch of numbers would be at every pixel, there is a color in there, and corresponding to every color, there's an intensity. So the first starting point could be, I could take an image and maybe I could represent every pixel as a color. All right, a very vanilla example could be either black and white. But then you have RGB images, which means that at every pixel, you might need to store 3 things: red color, blue color, green color. What intensity are these 3 things? Likewise, let's say you could have a text, and a very vanilla way would be, okay, I have a vocabulary, and I know that in my vocabulary, let's say he's the 4th index thing, right? So you could take he's a good boy and you could convert it into, let's say, a set of 5 numbers where each of these belong to, let's say, he, 3 belongs to is. Likewise, how would you think about videos? So videos is nothing but a sequence of frames, and every frame is an image. That's a very easy way to understand, okay, because I know how to represent my my image, I can easily represent the videos. Although, the space it will require and all of these things can be very, very could be very, very complex and very, very, very large. Likewise, song, how do you think of songs? So you could think of songs like as frequencies and in 2 different domains, like time and frequency domain. And then you could have like algorithms like automatic speech recognition that could convert speech to text, for example. And any algorithm that you can run on text, probably you can run on text, for example. Right. So there are various ways, and this is, of course, not exhaustive, but I just wanted to kind of drive home the point that these things need to be converted into some numeric form that a machine and that an algorithm can interpret and take actions on. Okay, over to the next one. Yeah, so I wanted to like really talk about some of these very things through very simple English. So for example, what is a model? So a model is nothing but you feed it an input and then desired output comes out. For us right now, let's think it's a black box. Likewise, right, what is representation? So how will an algorithm understand an image? So in the previous slide, I already talked about, so that term is technically always called representation, right? How can you flow all these inputs to this black box for all of that magic to happen? Likewise, right, how will the algorithm learn? So what does learning mean, right? So for example, so let's say for this input, you want this particular output, and you want to use that particular information that I know my input, I know for this input, I need this output, but my black box is producing some other output. So this means that I should have some way of tuning things such that my output from the black box starts gravitating towards the output that I desire, right? So there are a lot of terms filled in here, but long story short, like if you know what output you're expecting, then the idea is, can we calibrate? First of all, can we know how bad is the output of the black box from the desired output? So that thing is encapsulated through cost function. And then the other thing is, like, if you know it's bad, then can you turn some knobs to make sure that it's working better? All of this English, of course, is translated to math, but I wanted to get this general thing out. Likewise, right? For example, what if I really used one time when my black box was not doing well, out of a gazillion times, every time it does well, but I just took one example where it was not doing well and just use that example to like hammer this particular black box into submission. And lo and behold, it doesn't work well on the other, on all the cases it was working well before. So this means we cannot put extra emphasis on just few examples to tune our model, right? So the model should be able to do well by and large on many different kind of things. And we cannot shoehorn one model into doing well on everything. We cannot make one particular example the most important if it's actually not the case. Likewise, right? Like I said, I think I'm just quoting it, like proof of the pudding lies in its taste. So how does a model actually work on an unseen input? So, wait, it's able to do everything that I have shown it the data for, but what happens if it goes out in the real world and it has not seen something? How does it measure up, right? And how will you know whether it's time to get back to the drawing board and, like rethink some of these aspects of the model? And the last bit is like the inference headaches. Like, so does this black box really take too much time to process an input and spit out an answer? If yes, then, you might as well use that time for yawning. So I think there are some small aspects of every query detail of this is done through math and math, programming, analysis, a lot of that's why we talk about so many personas coming together to solve a problem end to end. Okay, over to the next one. Yeah, so I will come back to this, but long story short, the data goes in, then data engineers and have to build pipelines so that, more often than not, the raw data is not consumable by a model in its true glory. So you have to really enrich it, and you have to write pipelines, and imagine that this data could be coming thick and fast. So you have to write things that is able to handle the steady and incessant flow of data that might be coming, and you have to also make sure that that is consumable by the model. And then you have a model is trying to take that data and it's trying to learn from it. And then there is a component of optimization because you know exactly what output you wanted. So this means there's a lot of back and forth between model training and model optimization. This is the equivalent to like turning the knobs, if you will. And then once the model is out, then you want to make sure that so there are two ways. One is, of course, you have some data that you have never exposed the model to, and you want to get a sense of how the model will do on those unseen cases. That's one bit. That's called offline testing. But even after that, the job is not done. Between that is like, okay, what should I do in the real world? So you will like to launch that model in the real world, but not worldwide. So like Jayant had alluded to, like, or in fact had stayed quite a bit on, is like there's a need for experiments there. And experiment efficiency just means, okay, I'll divide the whole population or some bits of population into someone who will see inferences coming out of this particular model versus the previous model, and see how their behaviors diverge, and whether they diverge in the right direction, wrong direction, or there's no impact. And once all of that is said and done, and if you're lucky enough, then the biggest headache comes along, which is the deployment headache. And that deployment essentially means that things should be performant. It should continue to get monitored. It should continue to do well. And it should it should always be given the oxygen of doing well in the real world. And that's where a lot of battery people are employed. Okay, over to the next one. Yeah, so remember all the aspects I talked about. All of these aspects literally have a model component, and these model components could have interactions, meaning that I'll not go over every single thing, but let's say a query intent model. The input will be a query and the output will be the term that you need to search, right? Likewise, spell checker could be a wrong spelling came in and the output is like, okay, the right spelling comes out, right? Likewise, image searcher could be a query came in text and the output is like a list of images linked that to that particular query. And there could be interaction between these models, because imagine that you want to do an image search, you wouldn't want to do it on gibberish. So this means that probably a spell checker needs to work before that image searcher thing kicks in, right? And sometimes, so a lot of these things are, of course, are very like it's a mingling of a lot of systems, and all of these things feed into each other. So these are like, before you know, this becomes extremely complex. But thankfully, all of these things work out, and that's like what constantly people like us are trying to get towards. Over to the next one. So this is like Hangama Hai Kyo Barpa is one of my favorite ghazals, and I want to like, GPT definitely is like, one of the things that is causing a riot, and so I wanted to demystify some of this magic behind it so that our discussions could be more educated, and we understand that what is real and what is not. So let's go into the next one. So the magic is coming from something called transformer. And this was, by the way, started by Google, although GPT is from OpenAI. So I think they should tip their hat to Google also. Everything started from this particular paper. And so this is essentially called encoder and decoder architecture. And in a very simple language, encoder is interested with taking, let's say, a cat and making it into a bunch of numbers, feline and a bunch of numbers. And depending on how you train it, it should be able to understand. So you train it in a manner such that the two number representations somehow are closer to each other. So cat and feline should start becoming close to each other. King and queen, maybe they start like, getting close to each other likewise. And the decoder, in the diagram, the left-hand side is the encoder bit. The right-hand side is the decoder bit. So the decoder essentially takes the input and also takes the representation that came from the left-hand side, meaning these numbers, and it tries to spit out like after doing a bunch of math. So these blocks that you see, right, are stacked on top of each other. And at the end, what comes out is essentially, let's say, a probability vector. Now, to really drive home the point, imagine that this particular whole model is a translation model. And let's say cat went in, and we wanted a system that was trying to translate into Hindi. So Billy should come out. So the algorithm should actually place the highest probability on the number that is Billy in the Hindi vocab, right? So if you looked at the output vector, you will see that the 0.9 and that 0.9, right? If you look up in that dictionary where you have what is the number that what is the word that is associated with this particular probability, bam, Billy comes out first, right? So that's the broad idea that, you feed in an input, then you one part of it represents it in a manner that human beings cannot. And this, by the way, could be literally could be 100,000. Imagine, right? If you had to characterize a cat by 100,000 features, it will be impossible for you to do. But this algorithm is supposed to not always make sense. So not all of these numbers and dimensions will make sense to you. But in totality, they still mean that they are trying to characterize a cat. Okay, over to the next one. So this brought a revolution in NLP. It's more like an epoch. And likewise, this BERT was the beginning of semantic search, meaning that when Google started to understand more and more the semantics of what you're searching. So forget about the left-hand side, but the right-hand side is very important. One of the critical problems that was happening, remember, was we need input for which we know the output. But if you want to build models on like internet-sized data, right, you don't have the luxury of like people going and labeling every single example that you could lay your eyes on. So then how does the algorithm and these language models like learn to fill in the blanks? So this paper brought a revolution. So they carried on, like they use the same architecture for learning things, but think about cat is chasing a rat. And what they do is from just one single example, they create multiple examples. So for example, cat is, and then they will mask chasing, for example, a rat, and they know that the answer should be chasing for this particular. So if I fed the model and said, all you need to do is generate that word that needs to fill in the blank so that this thing becomes meaningful. Likewise, right, if you envelop the first one, dash is changing a rat, right? Cat is changing a dash, right? Think about all the sentences in this world, and you are trying to mask and trying to guide the model towards outputting something that makes sense and fits in, right? So this was the magic of BERT, that it went and created this. That's why the word generative means essentially the algorithm is trying to generate things out of either a prompt or it's trying to fill in, right? So it's taking an input and it's trying to generate another text, right? The P is for pre-trained. The pre-trained is because you want to learn these models beforehand. So, and how do you run beforehand on gazillions of data points? Some of this mechanism is through like the one that I'm showing you here. And imagine you can do like one-to-many mapping for so many sentences in the world, right? So you don't need explicit labeling. You don't need someone to go and tell, you know what, cat is chasing a cat is dash a rat, so it should be chasing. You have actual sentences in the real world. Okay, next. Yeah, and this is like, you know, the GPT paper that like, you know, that has been published and that we have all used, Chat GPT. And essentially, you know, there are three particular pieces to this puzzle. So the first bit is that, you know, you give a prompt. And by the way, for each of these, there are human labelers. So the reason this is very, very good is because they leveraged human help quite a bit. But that's not the only thing magic that happens. So for example, you explain the moon landing to a 6-year-old kid. So there were a battery of people who went, okay, for this particular prompt, what should be the output that we should generate? Right? So imagine that you did this on a tremendous scale for a lot of prompts like this. And then you try to learn, meaning that now forget about what, you know, the output that should be there for this given prompt. And now you're trying to entrust a model. So you know what, go ahead and learn it. You learn to generate the same output that this labeler is for this, all these prompts that I have given you labels for. So the first bit is like train, like, you know, on this labeled data set that has been assiduously labeled by these labelers, learn to generate. So the first bit is that particular piece. The second piece is this. Now for the same input, you must have seen this, right? In your interaction with ChatGPT, if you plug in the same thing twice, you will get different outputs, right? So why does that happen? So what happens is that, you know, for the same prompt, now because you have learned this model, so now you have a model that takes in an input and generates an output. But a lot of times these models are probabilistic, meaning that you could have generated the most likely sequence, you could have generated the second most likely sequence, blah, blah, blah. So this means that you have a lot of these, for the same prompts, you can generate a lot of outputs. And then there's another piece for where, again, they involved human labelers and they said, okay, I am giving you these 4 responses to the same prompt, go ahead and label them. So they did label them. Imagine how much taxing this might have been. But they wanted to automate this process. That is where this reinforcement learning, reward function learning comes along, where a deep learning model is interested to say, you know what, I've given you a given prompt. I've given you this bunch of outputs for the corresponding prompt. And you know exactly how you should rank them. Now this model is supposed to learn. So it is supposed to do exactly the same thing that the labeler is trying to do. Take the input and take the output and just give this output is rank 1, rank 2 with whatever likelihood, right? That Jayant already talked about. So so by this time they have learned 2 things. For any prompt, generate an output. For a prompt and given responses, learn how to rank. And the third part is the suppression part. So now imagine that a prompt never seen was given to this model. So the first model, the SFT model that we learned, like the first thing that will happen is, given that the prompt, the model will try to generate a given an output. Now policy in that output. And now what will happen is this reward function that we had calculated will essentially go ahead and give a reward to it, how good it is. So reward here is if it's very good, if it is likely to be accepted, that reward will be high for that model. And then you will see the interaction, right? So what will happen is, remember that all of these interfaces ask you for your feedback, right? So they have direct and indirect ways of collecting feedback, and they will use that particular feedback from you to go ahead and keep updating this particular policy. So this part in reinforcement learning is called policy gradient or policy changing, meaning that you change your policy depending on what you are seeing, the interaction. Okay, over to the next one. I think I'm kind of nearing the end. Yeah, so then let's say, right, in an ideal world, all of these things were fitting in and you saw amazing results coming out. So should you launch? Well, not so fast. And the reason is that, your model has seen only a small slice of the data probably, right? It has not gone out in the wild and tried to act. So then, although, not every company has the bandwidth, nor the impetus, nor the will to go ahead and do online experiments. But when we are talking of scales of like on the scales of Amazon or Google and all these behemoths, right? Then they don't blindly launch things. So idea is that, and one of the simple things is that even a simple button that you click on to buy something, the color of that also is decided through experiments. And whether it should be a tick, whether it should be a text, all of these simple micro decisions, right, are based on experiments. So nothing is arbitrary. At least that's what yeah, that's the case. And then the core idea is, right, and the core idea of experiments like Jayant has already said was that, can we study user output or behavior out in the open and see the impact of these metrics? Sorry. And and what you try to do is that, now you cordon off like, you ship these features and you don't tell them that we are using you as guinea pigs to test it. Otherwise they will become biased. So you have to do this very in a very surreptitious fashion, and so that you don't introduce biases. And then, like, you also want to make sure that you do some soul searching and make sure that you have not introduced bias without knowing about it. So for example, let's say you wanted to roll out a feature for all English speaking users worldwide, but you only tested it on the US users. An example could be, let's say, search terms in, you want to do very well on English search terms, but you want to do it very well everywhere in the world, India, everywhere. Now, India has a different kind of its own modifications of English, for example. If you only test it on US population, right, you might not have the full picture. Something might really work well on, in the US paradigm, and when you go to India, it might not work, and vice versa could also happen. So after going through this rigmarole of things, if everything looks plausible, you go ahead and launch. But again, not so fast. So the last bit and this puzzle is that, yeah, you can go to the next slide, please. Yeah, and so the decisions simply won't end. So the question is like how to serve these models, right? So will the input go to a model on the cloud? So for example, when you search, what happens, right? You plug it on your browser. Where does it go? Where does the output result come from? All these small things that happen in the backend. Then like I said, right, the user's data cannot leave the device, and let's say they want it, still needed ML. So for example, Google Photos is a classic example of that. Sometimes a lot, or maybe, things that happen in your own gallery, where you see Apple iPhone, right, categorizing your pictures, right? Nobody's sending your pictures to a cloud and doing it. It's happening on a device, for example. Or maybe the filters you're applying on your phone, right, on your pictures. Some of that is learned looking at the condition of your picture, right, whether it's dark, blah, 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 right? So, and then the other question is how many customers are trying to leverage that model at the same time? So this means, and from which geographies? So this means that the throughput considerations are also very important. That, how do you serve the interest of these customers who are maybe querying a lot versus querying less, right? Do you want to have dedicated servers for some geographies, blah, blah, blah. A lot of these questions need to be thought about. And the last bit is like, you don't want people to chew their nails while your model is trying to like think through an answer. So then how do you make these models fast? So like things like model compression, maybe you need better hardware for inferencing, all these different aspects are there. So like you can see, right, and I think I'm nearing the end, but at least from a ML perspective is like, you can see that there's a uses for people of different faculties and core strengths into these different aspects of one very innocuous looking problem. Okay, let's go to the next one. And now I'll end it. And if nothing works, right, then you can always come up with this dialogue. It's like, I'm to fakir aadmi, you pack your bags and leave. So I think by and large, even after doing all of this, you might still end up not being able to solve a problem, which is completely fine in science. you move on to the next one. So okay, let's and then we are coming back to the skills matrix where oh, by the way, I'll definitely try to first of all tell what these numbers mean, and then I'll leave the floor for questions and leave the floor open for questions, and also feel free, Jayant and Vivek can feel free to chime in. So yes, so for example, the data analyst, analytics, these different things that we have. Data engineer, for example, like I said, right, is interested with, by and large, with creating data pipelines where things are coming thick and fast, and you need to hash out these processed, consumable data from raw data. Data analysts might be like, okay, we already have a model out, want to see the impact it's bringing in the real world. Or maybe he's trying to scope out whether how big is the problem to be even start attacking that problem through AI, right? So that data analyst could be plugged in different life cycle of the project. He could be there for scoping, he could be there for seeing the impact, what have you. The ML engineer, by and large, is very interested with thinking about aspects like, how can I ensure that the model doesn't take too long? So how can I help the AI researchers compress his model or serve it on a hardware that is optimized for doing deep learning? So there you will see a lot of people working, let's say, NVIDIA and GPUs and these kind of profiles. The data scientists, I think Jayant can definitely talk a lot about it. My understanding of data scientists is like, by and large, they are they use a smattering of these different techniques, like, and they practically touch upon all these different aspects, and they are able to think about, they have to think about the business value of it, what makes sense. So they have to contextualize their solutions through a lot of lenses, and they have to they are not always interested with coming up with something that has never been seen before, or they might not always look at a problem that has not been solved before, but they still have to do the hard yards in terms of adapting it within the framework of your company. And you need to write very compelling articles about why your solution makes sense, prototype. A lot of these things happen, and much more. Probably Jen can talk about it. I can talk about applied science because I work in that area, and by and large, the mandate is that you are trying to solve a problem at a very big scale, on problems that are not very easy to crystallize and think about. There might be precedents, but you still need to read papers and design solutions and write prototypes, then work towards a model that works, and then work with engineers to make sure that it is deployed, all these other things, right? And also think about new ways of making sure that the model is robust. All these kind of things it entails a lot of reading, coding, different aspects. And there's a lot of, so all these personas interface with each other also. So that's also a very important thing to remember. Research scientists have a mandate, and they're very lucky because they have a mandate. They don't have the mandate like applied scientists who has to, you cannot blindly just wander in the research wonderland. So a lot of times applied science has to come back to the roots and say, you know what, you're here to make a business impact. So no matter how much research you do, you still need to come up with a solution that works. Research scientists has sometimes they're interested with like moving the bar too high. They don't have the burden of always coming up with solution that works, but they are interested with moving the frontiers of knowledge, and they are also very important. A lot of ideas come from there. So it's by no means it's an easy job or any less paid job or something. So and these different 5, 4, 3s were essentially just the competency level or the level of involvement you might need from these different fields like data wrangling and programming and what have you, in each of these different roles. With that, I reckon I have reached the end of my talk. And if you guys have any questions, then you can definitely direct them to me as well as Vivek or Jayant. Yeah, thanks.
Yeah, thanks, Parivesh. And Vikas, now you can understand, like, if this helps answer your question about, hey, this can be done by a data analyst. Yes, it can be done by a data analyst. But if you want to think about like you want to run some sort of, I don't know, like you want to implement an algorithm, you also want to run experiments. And usually data analytics people are not very equipped with the theory of experimentation, which is why you would need a scientist. But if you have a situation where you just want to implement it, yes, an analyst can do it.
things are also dependent on the level of ambiguity that you're handling. Am I? Yeah, so level of ambiguity that you're handling. So a lot of times you are thrust into situations where you don't know how to begin. You don't even have a good problem statement. So a lot of
Exactly.
times, like, so a lot of times I have seen, and I don't want to make any biased statements, but by and large, I have seen that depending on personas, the level of ambiguity you're dealing with, the level of preparedness you might need for handling that problem, all of these things can vary. But what I have seen in by and large is that, the more math you know, the more programming you have to do. You are thrust into situations that you have not seen before, and people are like really counting on you to formulate some solution to a problem that they are probably getting a hard time wrapping their head around.
Yeah, exactly. I mean, like
That's by and large the mantra, and what I have seen from my limited time here.
yeah, exactly. I mean, like if you go and usually like our first introductions, like there are courses as well, where the first introduction is you pick up a data set from Kaggle or something. It's a very well curated data set. The problem statement is very well defined. And the problem statement will not be like, hey, I want to establish a recommender system. It will be like, hey, I want to increase my sales. Then you have to think about like, how do you do it? What kind of techniques you could use? You could improve your like sales by maybe running your inventory tighter and moving things around. You can improve that by supply chain. You can do it by like purchasing from somewhere else. You can have like responsive capabilities. Like you can have what have you, right? But you have to think about like, okay, if I am zeroing down on like having a tight inventory, then you have to think about, again, I'm starting to get into retail, but net of it is like you have to, the more ambiguous the problem is, you have to think about like, okay, what problem area I'm going to hone into and how I'm going to solve it. And no one is going to come and tell you that, hey, you can use a recommender system to generate additional sales or whatever. So it's more about like dealing with ambiguity, which is where like some of these things come in here. Like communication is just not like bullshit talking. It's also like trying to talk to business to understand like how your business usually, at least for me, is a stakeholder. So it's more about just going and talking to them to understand what that problem is, what are they trying to solve for. And once you have a solution, you have to be able to communicate it back to them in their language. You just cannot show like a fancy like equation to them. Like you have to dumb it down in English.
And one caveat I forgot to highlight was that this field, of course, also has a lot of fluff. So what I wanted to also underline all of this talk by was that not every problem is solved. On AI/ML, all these data science, right? Things are not like a panacea for all problems, but it has the potential. If you formulate things properly, if you gather enough data, if you do your due diligence, you might have a good enough solution. And what is important to solve, what is important to ignore, all of these micro decisions are very important. So yeah, of course, that caveat is important, that this, when the field is hot, right, everyone comes in and thinks that it can solve everything. Even GPT-4 has its limitations. Yeah.
And I think Parivesh and Jayant can continue on the Q&As. And if someone has questions, like Vikas has my email, like just feel free to send it to us. But I have to go. Like I have like a 2-year-old, and she's starting to get cranky. Thank you all. I'll drop off. Parivesh and Jayant can continue, and then we can touch base later. And like we'll also include some more links. Like if you're interested in GPT, like I have like a very good like if you're seeing my screen, this is a pretty good like goes into English. The thing that Parivesh was talking about, it creates one word at a time the way we do it. So we'll share all these things that we have, and we go from there. And I'll stop sharing so someone else has to share if you need to.
I think we can take questions if we have. Yeah.
Okay.
Thank you.
Okay, I got to drop off. Thanks. Bye.
Yeah, if there are any questions, then feel free to ask them to Jayant, me, or otherwise we can just disperse.
They can also like send their questions on like the chat.
Yeah. Yes.
So we will be waiting for next 1 to 2 minutes for your questions.
Sorry, by the way, it was a very long session. I'm sorry that we transgressed the time, but I hope that you guys found tidbits of interesting things here and there.
It was quite interesting. Yeah, got to know a lot of things. So I think no one has any questions. So Parivesh and Jayant, should we wrap up?
Yeah, I think so.
Okay. So at the onset, I would like to thank Parivesh Bhaiya and Jayant Bhaiya for the hard work, and also Vivek Bhaiya, since he's not here, for the hard work they have done. Definitely, I was not expecting. I just thought that it will be just they will just be telling us just what we all know, and not be going such in depth. But what you all presented before us was very comprehensive, and if anyone is interested to go into data science, this master class, I would say master class will definitely help them to make that decision, that whether they want to go into data science or not. And even after that, if they have any question, they can definitely send us or to Parivesh Bhaiya, Jayant Bhaiya, and Vivek Bhaiya to get their queries solved. But I, on behalf of the Praktani Executive Committee and all the alumni, like to thank Parivesh Bhaiya, Jayant Bhaiya, and Vivek Bhaiya again for their hard work and for their time. It's I think early morning in the US, and so they have definitely skipped their very important sleep for us. So thank you, Bhaiya, for that. And to all the alumni who are present in this meeting, I would like to say that we regularly organize this session for you. So if you have any suggestions for our addas, and if you like to organize us adda on any topic, so you can definitely contact us. We will definitely try our best to bring best possible people. As you can see that these are the people like Jayant Bhaiya, Parivesh Bhaiya, and Vivek Bhaiya are one of the best in this area, and whatever you have learned are just top notch. So thanks again to everyone for joining us today. If anyone has any question, we will wait for 1 minute more, and after that we will just close the session. So thanks
Also,
again, Bhaiya. So yeah,
and
Bhaiya
also
can-
closing thoughts, I think, none of us can do well if we are constantly not getting any appreciation or patient listening. So I think as audience side, all of you guys were very good. So thank you. That gave me a lot of strength personally.
Yeah, Bhaiya, on personal level, I must say that it was definitely very enriching, especially the chat GPT part. And it started with very Vivek Bhaiya talked about very practical things, then Jayant Bhaiya delved a little bit deeper, and then you took us quite a lot deeper, and it was very stepwise, so it helped me grasp a lot of things in a better way. And we definitely have many appreciation in the chat also, MK Nishina sir from 1986 batch has written that it was an interesting session. I loved it. So
Yeah, no, thank you. Okay, guys, I think we have exhausted the questions that people had. So I'll let you guys go back to what you were doing before. Maybe the match is around the corner, who knows? Yeah, but
yeah.
thank you.
Thanks all.
So thank you everyone. Thank you, Bhaiya.
Bye.
Yeah.
Yep.
Bye, guys.
Bye.
Thank you.